In this video, we give the motivation for quotient groups and normal subgroups. Alright, in this video series, we're going to try to discuss normal subgroups and factor groups, also known as quotient groups. So we're actually going to start by motivating the latter. So the goal is to try to make a group structure on the set of cosets. So you're given a group G and a subgroup H. Why would this make sense? Well, you've already seen that integers modulo n form a group, and this other set of angles from pre-calculus forms a group. These are real numbers, where you say two real numbers are equivalent if their difference is a multiple of 2 pi times an integer. 2 pi times an integer is a subgroup of R under addition, and so this equivalence relation is technically talking about cosets. But we want to see if it's possible to do this in general. Given any subgroup H in G, we're looking at G mod H as the set of cosets. So remember, a coset with respect to an element G is the set of all elements G times H. Also known as elements in G that can be factored as little g times little h. For some little h. Or equivalently, those elements in G with the property that G inverse times x is an element in H. And then G mod H is the set of all cosets. By analogy I've made before, one way to think of these is a coset is something that is parallel to the subgroup H, and the set of cosets are all the parallel lines. So let's try to turn the set of cosets into a group. That means given two cosets, one's represented by little g, the other one's represented by some little g prime, we want to get a new coset as their product. Well, one thing that might make sense is to just multiply g times g prime. And if we take that as the definition of multiplication, associativity is easy to show. If I take three cosets, this product of three cosets is easy to calculate. It just ends up being this thing here. It's the coset whose representative is the product of the three representatives. To see that, if I multiply the first two cosets together, I get a coset whose representative is g times g prime. Now if I multiply these two cosets together, I get a coset whose representative is g times g prime times g double prime. Now if I go in the reverse order and take the product with the other parenthesization, the same thing's going to happen. If I multiply the last two cosets, I get a coset whose representative is g prime times g double prime. And then if I multiply these two cosets, then I get this triple product. And then we have equality here because these two elements are actually the same because of associativity in the group G. And so we do have associativity. But we do have a question that I should have asked first. Is this operation even well defined? What am I doing? I'm defining a new coset in terms of these two given representatives. That's like saying, one way to think about this doubt I have is you could think of a coset as being a dice. And the elements of the coset are the different labels on this dice. And what I'm doing is I'm defining a product operation by saying, take two sides of each of these dice, multiply their labels together, reach into your bag of dice, and find a new dice that has that label on one of its side, and define that to be the product. Because you can think of this set of cosets as being a bag of dice. And of course, the question of well-definedness is that, well, if I actually chose a different face on these two dice, how am I guaranteed that I end up with the same dice at the end? How come, is it possible that I don't end up with a different set of dice? In other words, if I used h and h prime, is it the case that I actually do end up with h times h prime, that the product of these labels ends up being on the same dice as this label? That's the problem we have to check. To illustrate my point, let's take this following example. G is the symmetric group on 3 letters. H is the subgroup generated by the 2-cycle 1, 2. So it only has 2 elements. You can check that G mod H only has 3 cosets. Here is one choice of 3 representatives. Notice that the remaining 2 representatives are as follows. These 2 cosets are equal, and these 2 cosets are equal. So let's multiply these 2 cosets together. According to our operation, the result is what happens if I multiply their representatives together. And the 3-cycle 1, 2, 3 and the 3-cycle 1, 3, 2 are inverses of each other. So this product is the identity. But on the other hand, I should the first coset is equal to 1, 3 times h, and the second coset is equal to 2, 3 times h. This is my point. I'm taking a different label on the same dice, so to speak. I should get the same dice left over. So now let's compute this product. Instead, the coset representative is 1, 3 times 2, 3, and you can check that that's 1, 3, 2. And so we see the product is not well defined because here, if I take these 2 coset representatives, I get this coset. But if I take these 2 coset representatives, I get a different coset as my answer. So my answer depends on my choices, which coset representatives I pick. Therefore, it is not a well-defined function from pairs of cosets to the set of cosets, because I get more than one possible answer, and you should only get one answer. And that's what it means to be well-defined. A well-defined function is a function. If it's not a function, then it's not well-defined. So this is what we have to deal with. So the question is, what property do we need in order to ensure that this actually happens? Alright, so let's see what we need as a requirement for well-definedness. Well, let's just assume the operation's well-defined and see what happens. And to simplify the calculations, I'm just going to only focus on well-definedness with respect to the first coset. Suppose AH is equal to BH, and suppose you have another coset CH. What conditions do we need to force ACH to be equal to BCH? So notice here, I'm only talking about multiplying like that. Oh, what does it mean for AH to be equal to BH? Well, that means B is an element of the coset AH, which means B is equal to little a times little h for some little h and h. What does it mean for these 2 cosets to be equal? Well, it means AC inverse times BC is an element in H. AC inverse can be written as C inverse times A inverse. We can replace B with AH here to cancel out the A's. And so we see that we arrive at this condition. We need C inverse HC to be an element in H for well-definedness with respect to this particular case. But we want this to work for any pair of cosets. So once you fix AH, you're going to get all possible equalities here by letting little h here vary over. You're going to get all possible b's here by letting little h vary over all elements of the subgroup. So in order for this well-definedness to hold for all equalities of this form for fixed A, we see that we need this condition for all elements in H. And for all C, for A fixed. Of course, once we have that, then we see we no longer need to talk about A being fixed. A can be any coset, because A no longer pops up in this formula. And so for any equality on the first coset and the second coset varying, we actually do have well-definedness as soon as this condition is satisfied. And we'll see in another video that this is actually enough to get well-definedness in general. So by assuming that we are well-defined in only a special case, we got this special condition. And this special condition is the definition of being normal. H is normal. And we'll discuss that in another video. So the main punchline is that sometimes for quotients, for cosets, you can define a multiplication, and it's well defined only when H has this special condition. Otherwise, you do not have a well-defined group operation on the set of cosets.